Right, we're skipping the usual intros today because we need to talk about something incredibly urgent. If you're sitting the Cambridge International AS and A-Level Biology 9700 exams, Section 12.2, the Krebs cycle, and specifically that tricky transition from oxaloacetate to citrate and decarboxylation is honestly notorious. Principal examiners are practically screaming that this is one of the most misunderstood areas in the entire syllabus. You could know the biology perfectly, but you might still be hemorrhaging marks. So let's fix that right now in this explainer.
Imagine you're sitting in the exam hall right now. You're asked to explain the sequence of events as oxaloacetate is converted into citrate. You confidently write down the steps, you name all the molecules, and you breathe a massive sigh of relief. But what if you just drop 2 entire grade bands because of one tiny, almost invisible logical error? Can you spot the exact mistake that cost top candidates their A grade right at the start of Section 12.2?
Well, here's the cold, hard truth straight from the examiner's red pen. The mistake is flawed reasoning. Specifically, it's confusing the cause and effect sequence when oxaloacetate converts to citrate. Examiners consistently report that students are losing easy fundamental marks because they just list the biological facts but totally fumble the causal sequence. They state what happens, sure, but they mix up exactly what causes what in this critical multi-step pathway. And that perfectly sets up the multi-step trap, and exactly why your ordinary everyday revision just fails under exam pressure.
Think about the exact academic benchmarks Cambridge is using to assess you. The syllabus doesn't just want you to memorize the Krebs cycle like a grocery list. It requires logical, structured reasoning. The assessment framework completely prioritizes analytical depth over superficial breadth. They demand a connected, conceptual understanding. And honestly, the most important part is your ability to transfer that understanding to completely unfamiliar contexts. If you just memorize a textbook paragraph, your logic is going to fall apart when they throw a curveball at you.
Okay, so how do we actually beat this? Let's get into the method mark strategy.
You absolutely must follow the standardized sequence to secure maximum points, because examiners award crucial method marks for this exact logical progression. Step 1. Identify the key elements of the pathway. Step 2. Apply the relevant biological principles, like enzyme action or decarboxylation. Step 3. Execute your analysis with really clear, explicit working. Do not hide your thought process. And finally, Step 4. Verify your results. This is exactly how you prove to the examiner that you're processing the science, not just regurgitating it.
Now hang on a second, because in just a moment, I'm going to reveal a hidden examiner clue that changes the answer completely. It's a secret, literally hidden in plain sight on your exam paper. But before I show you that, you need the framework that actually makes this clue obvious. Otherwise, you're going to walk right past it.
To build that framework, we need to look closely at principal examiner warnings. This is where we learn what goes wrong across thousands of papers.
These are the top 3 exam-ruining mistakes in Section 12.2. Number 1, like we just talked about, is confusing cause and effect in the cycle. Number 2 is a really tragic one, just forgetting to check units and terminology. And number 3, providing answers that are super generic and not specific to the context given in the question. If they give you a specific cellular context or maybe an unfamiliar organism and you just paste in your generic Krebs cycle description, you're getting a 0.
Which brings us to a massive terminology alert. The examiner reports clearly show that candidates constantly confuse key terminology. You've got to explicitly define your key biological terms before you use them to build your extended responses. Don't just toss the word decarboxylation into a sentence and cross your fingers that the examiner knows you understand it. Establish the definition first, and then build your causal chain.
All right, time to put your examiner hat on for a quick interactive challenge. Let's spot the error.
Think about 2 wildly different ways you could answer this. A flawed approach vaguely describes oxaloacetate converting to citrate. It might drop a few biological buzzwords, but it completely misses the definitions and the unique context of the question. That is just superficial breadth. Now compare that to a top-band approach. It executes the method mark strategy flawlessly. It's precise, it's step-by-step. It establishes the cause, it details the effect, and it clearly defines those key terms before explaining the biological pathway. That is exactly what analytical depth looks like.
But hey, mastering the theory is really only step 1. Now we need to look at mastering data and evaluation, because this is where the highest grades are won or lost.
When you're hit with a data-heavy Krebs cycle question, maybe it's a practical experiment measuring respiration rates, you need a rock-solid data interpretation sequence. Step 1. Extract the specific data from the tables and graphs. Step 2, interpret the relationships between those variables. Step 3, calculate the relevant statistics, whether you're running a t-test for comparing means or maybe a chi-square test. And Step 4, draw conclusions that are strictly based on the hard evidence you just analyzed.
To snag those absolute top marks and really show off your evaluative thinking, you can't just calculate, you have to evaluate. The best candidates question the underlying assumptions in the experimental design. They consider totally different analytical perspectives. They evaluate alternative interpretations of the data, and they relentlessly justify all their scientific decisions with hard statistical evidence. That is the secret to hitting those top descriptive, analytical, and evaluative mark bands. Listen to this direct quote from the Principal Examiner report. Candidates referencing cross-topic connections achieve significantly higher marks. Guys, this is literally a cheat code. The Krebs cycle does not happen in a vacuum. Connect section 12.2 to enzyme kinetics, to cellular structure, or even to genetics if the context allows for it. Showing integration across the entire syllabus proves that you have true conceptual mastery.
Okay, so we've dodged the biological traps. You've got the theoretical framework, you know how to process data, and you know exactly what the examiners are warning you against. But what actually dictates the final mark band you land in? Why do students with absolutely perfect biological knowledge still walk away with 0 marks on a 6-mark question?
Well, here is the resolution to that clue I promised earlier. The hidden cause of those lost marks? It isn't the biology at all. It's the command words: describe, explain, calculate, evaluate. If a question tells you to evaluate and you just describe the Krebs cycle, you get nothing. It doesn't matter how flawless your description is. Misunderstanding the command word is the single biggest reason perfect biological knowledge fails to score.
Seriously, are you going to let a single misunderstood command word rob you of your A grade? You just can't afford to lose those marks. You need to know exactly how to decode these command words before you ever step foot inside that exam hall. So next up in our Explainer series, we're decoding the command words that decide the mark band, showing you exactly how to tailor your flawless biology to the examiner's specific demands. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. See you in the next session.